Welcome everyone to lesson 3.4 Precalculus, which is all about the graphs of sine and cosine. So we've been dealing with sine and cosine as ratios for right triangle trig. Now we're going to treat them as functions and identify and use some behavior of them. So let's get started. Our definition of the sine function is going to be given an angle in standard position on a unit circle centered at the origin. We're always going to have a point P somewhere along the circumference of the circle. The sine function is defined as the y-coordinate of that point, depending on what angle we're using. So there's a really nice graphic here. If our angle is t and we have a point on the circle that's AB, sine of t is going to equal b, no matter where that point is on the circle. And I think that's awesome. So what I have here for us is I actually have our chart from the unit circle filled out for both exact values and approximate values. The approximate values so we can graph it and actually look at what this thing looks like. If we're dealing with a circle, wouldn't it be cool if you had like half a circle and then half a circle and then half a circle and then half a circle? Wouldn't that be awesome? Let's see if that's true. Let's see if that works out that way, because I think that would be really, really awesome. So let's graph this, and we're starting at 0 at 0. So we get this, and we're essentially going to be mirroring this throughout. So what does that look like? Well, try to connect them as smoothly as you can. I don't always do the best of jobs. But we should end up seeing this beautiful, 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 beautiful S-shaped curve. And it's not quite a circle. It's not quite as pointy as mine is, but it's not quite a circle. It's almost parabolic. It almost looks parabolic. It's not a parabola, but it almost looks parabolic, which is really, really cool. So sine makes an S curve. And it's going to repeat this S curve forever, because if we keep going around the circle, we're going to get the same Y values, right? So the period of sine is 2 pi. So it's going to repeat that behavior every 2 pi. So let's examine its behavior for one period and really break down what's going on here. So increases, decrease, concavity, up, concavity, down. We're going to end up with this behavior. So we have this beautiful S-shaped curve. And I do mean beautiful. I'm going to keep saying it. It's gorgeous. Mwah. It increases. If we look at the graph itself, the graph increases from 0 to pi over 2 and 3 pi over 2 to 2 pi. What does it look like on the circle? Well, think of y as the y-coordinate of the point on the circle as the sine function. The y-coordinate gets larger on the right side. So that makes sense. So anytime that we're on the right side of the circle, it's increasing. Decreasing would be the opposite, right? It's decreasing from pi over 2 to 3 pi over 2, which just so happens to be the left side of the circle. It's going down. The y values are going down. Concavity is also quite interesting. So it's concave up. We can look at it. It's concave up. It'll hold water between pi and 2 pi, which just so happens to be the bottom of the circle, which also looks concave up. And it's concave down from 0 to pi, which is also where the circle itself looks like it's concave down. And I think that's really, really cool. And it's also, I think it's just so interesting, really, that even though we're dealing with the height of a circle, given an angle, we didn't actually get half circles here. We got something much stranger, much more intricate, much more beautiful, if I'm going to be honest. So how do you graph these functions? You're going to be asked to graph these functions a lot. Oh my goodness, it's going to be so much fun. But when you graph them, and I've always taught them this way, I highly recommend the 5-point method. So if you notice, in our sine graph here, there are 5 key events that happen. Sine started in the middle. So it starts in the middle, goes up to its max, goes down to the middle, goes down further to its minimum, and goes up to the middle again. So, and I've been using hand gestures here recently. You go middle, up, middle, down, middle. So that's what sine does. And it does it evenly. It's perfect. It's so beautiful and intricate how this function works. So it goes middle, middle at both of the ends. Directly in between the two middles is a middle again. So between 0 and 2 pi, the direct middle of that is pi, and it's in the middle. In between the first two middles, directly in the middle, between 0 and pi, is pi over 2. It just so happens to be a maximum at that. In between the second two middles, pi and 2 pi, which is 3 halves of pi, is a minimum. I think it's just beautiful how that works out. But if you can memorize this, that it goes mid, up, mid, down, mid, you're good. You got it. That is sine. That is the S-shaped curve. That is beautiful. So, knowing that, let's determine what's the behavior for these given angles. So if I have an angle that's in between pi over 2 and pi, what's the concavity? Is it increasing or decreasing? Like, what's going on here? And there's a lot of different ways to handle this question. And in fact, I want to try to talk about each of the different parts in a different way. And maybe one of those ways just resonates with you a little bit more. So if I think about this angle is quadrant 2. So I'm going to draw that. What's going on here as I go from, the smaller angle to the larger angle? Well, it's decreasing and it's concave down. So this is decreasing and it's concave down. Let's double check. Pi over 2 to pi. Pi over 2 to pi, it's decreasing and it's concave down. Isn't that awesome? So you can just draw the part of the circle we're talking about and you got it. Something else you can do is you can draw a rudimentary sine curve based off of our 5 key points. We know that we're going middle, up, middle, down, middle. We're making an S, right? And each of those is a quarter of the circle. So if we're going from 3 pi over 2 to 2 pi, we're talking about this part right here. What is that? Well, it just so happens to be increasing, and it happens to be concave up. Not too bad. The last one here, we have pi over 2 to 3 pi over 2. That's more than just a quarter of the circle. That's a whole half of the circle. So I'm going to go back to the circle part, and I'm going to draw that. That looks like this, right? So if I notice the whole time, it seems to be decreasing the whole time, but it's not concave up nor concave down the whole time. So the concavity, help if I could spell, changes. So it's not the same. And that's 2 major ways to do it. If you can think of more, I could also think of triangles and how the triangles would change. Use what's best for you. And if you come up with something better, share it with me. Share it with the class. Love to hear some of your ideas. That is the sine function. It sounds super scary, and it might have been super scary if you were introduced to it in Algebra 2, but it's not. It is just a beautiful curve. So, what is cosine then? Well, if we take the definition of sine and expand it to, instead of the y-coordinate of the point on the circle given an angle, it's now the x-coordinate, which makes it, instead of the height of the point, makes it the width of the point, and we get the cosine function. So it behaves in a very similar manner. In fact, we're using all of the same points, just in different locations. And again, I think that's so cool. So let's plot some points. What does this curve look like if I complete it? Bear with me, it's going to look awful. So, actually, nope, I missed it a little bit. I can't see, I'm right-handed. We get this, which mirrors the sine curve a little bit. If I were to extend it, you would start to see that S-shaped curve. But if I rotate it, it kind of looks like a C. So it looks like a distorted C. So cosine, I'm going to put quotations around it, C curve. It's an S curve. It is. If we just continue it and paste it together, it will look like S's, but they kind of look like C's, which I think is nice. So sine looks like an S, and cosine kind of looks like a C if you squint real hard and turn your head to the side. But I digress. So again, it's a beautiful curve. let's look at the behavior of this curve. So its behavior is going to be very similar in the fact that we're kind of dealing with quadrant by quadrant, but when each thing occurs is going to be a little bit different. The period is also 2 pi. It's going to repeat itself, follow the same cycle every 2 pi. But when is it increasing and decreasing and so on and so forth? So cosine is increasing from pi to 2 pi. And how do I see that on the unit circle? I'm looking at the x's. The x's go up from here to here. So again, I'm looking at the horizontal side of it now. So the x's go up from left to right. I'm going left to right when I'm on the bottom half, which is pi to 2 pi. It's decreasing on the top of the circle where I'm going right to left. So that is when we have 0 to pi. So 0 to pi, I can see it's decreasing. That makes sense. Concavity. We kind of saw the bottom of the circle was concave up for sine and the top of the circle was concave down for sine. Twist it. Because we're dealing with the top, the upper part is here. So our positive on the right side of the circle, that's when it's concave down. And it's concave up for the bottom of the turned circle, which would be the left-hand side. So that's kind of where we can see the circle come into play. We just got to like tilt our head a little bit or turn the circle. So not bad and follows the same behavior. So hopefully we're not feeling awful about it. Just like sine. Oh, I didn't change it. Oh no, cosine. When graphing cosine, we also have key points that we can use, and I highly recommend. But sine, so recall, sine was mid, up, mid, down, mid. Cosine is up, mid, down, mid, up. So again, you can't go to the top or bottom without going to the mid first. So it starts up, mid, down, mid, up. So it's starting up and ending up. So the beginning of its period is 0, ending of its period is 2 pi, 1 and 1. Directly in the middle of that, in between the two maxes, is the minimum. Directly in between the mins and the maxes are the middle, is the mid, which by default is 0. But there's a reason I'm saying mid, because when we start to shift it, the mid is going to shift, so it's not always going to be 0. But I did start off, when I did teach it before, I was like, it's 1, 0, negative 1, 0, 1, or 0, 1, 0, negative 1, 0. I like the hand signs. 1, it kind of gets our motor skills in the encoding process, but whatever floats your boat. You are the master of your own learning, so you should know, hopefully at this point, what works best for you. And I'm just trying to give you more tools in your toolbox. So let's continue, shall we? So just like we did with the sine, we can identify behavior off of cosine just by looking at the curve itself or by looking at the unit circle. So let's do both again. So if I'm looking at this part of the circle, this is quadrant 2 of the circle. So if I go draw quadrant, if I draw quadrant 2 of the circle and I'm going this way, what's happening to my x values? My x values are going lower, so we are decreasing. But if I look at the concavity, if I tilt my head to the side, it would be concave up, because it's on the left side of the circle. Next one, we can actually do the 5 key points and draw a crude little cosine graph. Remember, cosine is up, middle, down, middle, up. So we get this crude little curve, and we want this part of it. Well, I can see there that it is increasing, and I can see that it's concave down. Not bad. I'm going to go to the circle again for this part. We're again dealing with quadrants 2 and 3. What's happening here with the x values? Well, the x values are decreasing and then increasing, so you can't really, it's both increasing and decreasing. Concavity, though, it's this part here, which, when you rotate it, would be concave up. And if you're not seeing that connection, please ask me in class. It's really important that we understand our basic behaviors for our basic functions, because when we go manipulating them in future lessons, we need to understand how they're working, because we can understand our manipulations a little bit better based off of how the parent or the default function operates. So here we have a nice little, like, actual meaty question here. So we're given an angle theta, and that's the one pictured here. And then we are given a function g evaluated at alpha that is equal to the sine of alpha. And we want to know for what angle alpha would this be true? Oh, no, so this is true. Which of these would be true? So we know that alpha is bigger than theta. So alpha is somewhere in here, but not quite up to the quadrant angle. So what would be true? Well, we're talking about sine. We're talking about the y value, right? So we're caring about the y value of these points. So we have x comma y, and then x comma y, right? We care about the y's. And this is alpha. This is 3 pi over 2, and this is theta, right? Which one's true? Is the y of alpha less than the y at theta? Y of alpha is definitely lower. I think that might be true. Is the reverse true? Definitely not. Are they equal? Definitely not. And does it change? Well, it would change if we didn't have 3 pi over 2 being our, halt, being our stopping point. So because we have the 3 pi over 2, it's not going to switch. It's only A. That is it for us. So if you have any questions, especially with the last one or anything at all, really, please make sure you ask. Otherwise, I'll see you in the next lesson.